Fine. So, welcome to this seventh lecture of nonlinear control theory. And we carry on. Okay, Radu, maybe you're familiar because I remember you used to be B1. So probably Radu is familiar with this the stuff we are going to talk now. So we are going to talk about n-dimensional systems. So what we did, let's do a short recap of the things. So if you remember, we started talking about nonlinear dynamics, essentially weak nonlinear dynamics, weak nonlinearities, okay? Dynamical systems of differential equations whose functions are smooth, okay, are nice functions, and we defined the concept of solution for first-order systems, then we extended everything to second-order systems. Once we had the solution concept, we could discuss notions such as equilibrium and stability, okay? And we saw the very simple but non-trivial case of first-order systems. Then when we found the notions of a stable equilibrium point and unstable equilibrium point, and we emphasized that stability is not a property of the system, but a property of the trivial trajectories of the equilibria, okay? And then we extended the discussion to the more important case of second-order systems, where we found that using a first-order approximation and taking very small variations of the system around the equilibrium points, we can understand the behavior and we can actually draw the behavior of the nonlinear system around the equilibrium points. And we found several very nice cases and very nice drawings we had. We had those configurations of stable or unstable behavior such as node and focus for the equilibrium point, okay, depending on what? Depending on the types of eigenvalues of the linearized system, okay? And then we found out that there's also some phenomena which are peculiar to the nonlinear systems, when, such as the center behavior, which is undecidable because it's not structurally stable, so you can't tell exactly how the nonlinear system behaves when you have something such a when you have a variational behavior such as the center behavior. And then we emphasized, okay, another structurally stable type of behavior, which is very peculiar to nonlinear systems and very useful to engineering, the discussion about stable oscillations. Stable, robust, if you like, and untouched by perturbation oscillations. And that's limit cycles. That's typical to nonlinear systems. And the last example we discussed in the lecture, and then you also have some assignments, and you also we also showed in some MATLAB files, we have the van der Pol oscillator. This is very interesting because this simple polynomial second-order equation, okay, denotes or has very nice. It's very interesting, you know. It's a bit counterintuitive, if you like. Why I'm saying that? Because, for instance, the pendulum equation contains here in the elastic force equation contains a sinus. This one does not contain any sinus whatsoever, but this is oscillating, whereas the pendulum doesn't oscillate constantly. But this guy, okay, under specific assumptions, okay, on its parameters, this guy actually behaves in steady state, if you like, exactly like an oscillator. So the equilibrium, okay, is not necessarily stable, but the final behavior is constantly sitting on a closed curve, hence exhibiting oscillations. And this is very important and very interesting, okay? The van der Pol oscillator. Now we are going to talk about, we are going to extend this to the case of nth-dimensional systems, and we are going to pose a good problem, and we are going to ask ourselves, okay, now in the nth order systems, you can't have phase portraits any longer because the state space now is Rn, as it's written here. So the state space now is very abstract, is Rn. So we can't have drawings, we can't have nice graphs any longer. But we can have some theoretical, very important theoretical results. And these theoretical results actually are encompassed by what is called Lyapunov stability theory. The Lyapunov stability theory. And we are going to make a very nice link to what we discussed in the previous chapter, okay? And we'll see that because in the previous chapter we touched the subject of energy and constant energy variation, okay? So we are going to do the same here and we are going to extend this idea of constant energy here and define the notion of stable, exponentially and asymptotically stable equilibrium point. And Lyapunov will help us with some very nice, unfortunately only sufficient conditions on the stability of an equilibrium point. Unfortunately, they are not at all necessary, and that's why Lyapunov's stability theory is so complicated. And that's why determining a Lyapunov function can be a very tedious and very intricate task. Okay? Right. Good. So the state space for nth dimensional system is now Rn. We have functions of several variables, not only two variables, but several variables. F is a vector field on Rn. Okay, F is a vector field on Rn. Okay, so we consider now a function f defined on a domain of R times Rn. This R is for the time dependency and Rn is for the state dependency. Okay, with values in Rn, a continuous function on this domain, and we consider the so-called non-autonomous, but well, here it's it's autonomous system actually. But I think this is not non-autonomous, but actually wanted to say time variant, because this is actually time variant. You don't have any input here, but you have the time dependency. You have this time variant system of this form. However, since we are talking about, we are going to treat the case of time invariant system. We are going to treat the case of time invariant systems, okay? Because this makes the discussion very easy. Well, whatever easy means. It's not easy, but simplifies a little bit the discussion. Okay, we consider that all the components fi of this vector field f are continuous or continuously differentiable. Okay, we need that. Why do we need all these things? Because we are going to define, as we are familiar with, a concept of solution. Okay, it says here a little bit of philosophy. It's the name of this slide. It's a mix of Romanian and English stuff. All that is exterior to things, the mathematical symbols are always actually, well, whatever is external, the mathematical symbolism is, however, the same, no matter how many external things you have. That's what it says. So the idea is that we are trying to make a unitary theory, okay, of these kind of systems, irrespective of the field where they come from, just like we did so far. So we do not care that our second order systems are mechanical or electrical or whatever. It's all the same. The theory is unitary, is one and only. Okay, so we have systems of differential equations which can define a physical system, and conversely, a physical system which can determine a set of differential equations as its model. Okay. Well, the differential equations have solutions. Okay, mathematically. Well, in the systemic approach, this is called an evolution of the system. Okay, an evolution of the system. So the solution determines an evolution of the system. However, conversely, the evolution of the system gives a solution of the model of the differential equation. Okay, And of course, we have to ask ourselves, we have to wonder, is the model valid? That's the biggest question of all. And that's a question we've been carrying throughout the entire lecture. Okay, you build a system, but is it valid? Okay, because if you want to solve the differential equation, this is a mathematical Cauchy problem. This is the Cauchy problem. Okay, but physically, you observe behaviors. So what's the relation between what you measure or observe or simulate and the solution of the mathematical equation? Okay, so this is the main question we have to ask. Okay, so what's the relation between the two faces of the problem? Okay, which is nicely written here, the mathematical part and the physical part. Okay, so, but well, mathematics is going to answer to the is going to provide a very nice answer to this issue, because we are going to use the fundamental theory of differential equations. Okay, we are going to talk about the existence of solutions and uniqueness, and we are going to give without proof. Of course, we are going to present and we are going to state that indeed, under specific assumptions of continuity or differentiability, such a system has a solution. Of course, like I always mention, all these results are local and not at all global. Okay, and we are interested, of course, in the continuous dependence on the initial conditions and the parameters. And this ingredient is what helps us define, for instance, stability. Based on this, we can formulate concepts such as stability. So this is what we have to settle and to understand. Okay, this is what we have to settle and what we have to understand. Okay, so now, of course, we are going to have main results. Yeah, we are going to have main results. Right. Existence, first of all. Okay, the existence. Okay, we have a domain defined like this with two variables, time and x, two big variables, so to speak. So it's actually n plus 1. Yeah, because the state space is Rn, so x is in Rn and t is of dimension 1, such as, and we fix a t0 such as the distance between the time moments t and t0 is bounded by some sigma, some very small sigma. Okay. Right. And such that x and x0 are very close to one another, and they are bounded by in a ball of radius r. And we define m, the maximum value of the norm of f. Okay, so we define some mathematical ingredients. So as equation 1, which is this one, equation 1 has a solution x depending on the time, on the depending on the time in general, on the initial moment t0 and on the initial condition x0, on the interval on an interval of length 2 tau, verifying the existence of the initial condition. Okay, verifying the existence of the initial condition. So equation 1 has fixing an initial condition and an initial time. In a very small neighborhood of the initial condition, we can have another solution which is different from the initial condition. Okay, all right. One can identify the evolution of the physical system, they say here, with the solution of the corresponding differential equation. Okay, that's what you can do based on theorem 1. That's what you can do based on theorem 1. So we do have existence. We do have existence. Okay, so a local solution exists. A local solution exists. The second result is about uniqueness. If the solution is unique, that's what we have to ask ourselves. And of course, it's the same result that we saw in the first order and in the second order case. So we assume that F verifies some Lipschitz condition on the domain, on the definition domain. Okay, and the Lipschitz condition looks like this. There exists a function L depending on the time, if you see here. So it's not a constant. Okay, LT positive, such that for every point Tx and every point Ty in the domain D, such a condition holds. This is the Lipschitz condition. Okay. So what you see is that the difference between the values of the function is bounded by the distance between the points. Is bounded by the distance between the points. So that means that the evolution exists, so to speak, and the evolution is bounded by this Lipschitz function. Now, if this condition is satisfied, and if you have two solutions, x1 and x2, okay, such that at the initial time, the initial condition, both they have the same value, then both solutions are well defined and they're actually one solution. They're actually one solution. So the solution is unique. So if you do a small variation, very small variation, and the function is Lipschitz, actually you recover, and if you start from the same point, from the same initial condition, then you get the same evolution. This is actually the meaning of this result. That's what it says. That if you start from the same initial condition, and F satisfies the specific Lipschitz condition, typically the solution of the differential equation is the same if you start from the same initial conditions. Okay, so the solution is unique, local, again, local result, both of them, existence and uniqueness. Okay, local results. We cannot give global results. Okay, can't have that, but we can have local results. So the idea is that the system is deterministic. Okay, F is Lipschitz. F is, we know we don't have no stochastic parameters. Okay, no weird parameters in our F. And the main idea of theorem 3 is that identical initial conditions determine identical evolutions. That's what I kept mentioning. That's what I kept saying. So the solution is deterministic, and if the solution is deterministic, then the evolution is unique. Okay. And the final, another result, very important result, is that we can show that we have a continuous dependence on the initial conditions. This is very important, because if you do not have that, and in the initial conditions you have discontinuities, things do not make sense. Okay, not in this context. So essentially, you have to redefine all the concepts of solution, uniqueness, and so on and so forth. Okay, so if F is Lipschitz, whatever, then any solution is continuous with respect to x naught. With respect to x naught, that is for any epsilon positive epsilon and any time t in the interval I, where the solution is well defined, there exists a constant delta such that if two initial conditions are close to one another, then the two solutions are also close to one another. So what the remark 6 is explaining the result in theorem 5. So small measuring errors in determining the initial conditions or small variations of the system parameters produce small changes in the evolution of the system, at least for a short time. So small produces small. And this means the continuous dependence on the initial condition. And now, gathering all the results discussed so far, we can draw the conclusion that the mathematical models described by differential equations are consistent and yield well-defined mathematical problems. So we are in a legal context for all we're going to talk about from now on. From a mathematical point of view, everything is legal, everything is all right. And this is very important. This is very important, okay? All right. Okay, let's have a short break, and after the break, we are going to discuss stability, because after you have a solution, stability is the main feature you want to have discussed. A short break, and we'll meet again. I'm back. Hello, everyone.
Hello.
Hello, I'm back too.
Stability, yeah? Um, the first idea, okay, how to define stability, or how people or how engineers um, have the perception about stability. It's based on the what we have defined as the continuous dependence on initial condition, okay? So delta in 5, this guy here, explicitly depends on the finite interval where the solution is defined. It's expressed here, okay? That's why it's called delta index I epsilon, okay? For larger intervals, delta has to stay sufficiently small. Hence, the delta in 5 does not depend on time, okay? To be in the range of the measuring errors. So the measuring errors do not depend on time, and the any errors that might occur, okay? The evolution comes back to the clear and the good solution. So this is one way to think of stability, okay? In the sense that if you do a perturbation in the initial condition or in the parameters, the solution essentially stays the same, okay? The solution stays the same. That's one way to look at things. The second idea, and this is the idea where we are going to base all our arguments on, is the existence of a so-called perturbed reference solution, okay? Okay? So we have a specific evolution of the physical system related to some phenomenon, it says here, corresponding to a particular solution of the differential equation. This is called the reference solution. This is called the reference solution, okay? Okay, so this is the in figure 1, you can see there, yeah? This is, you see here, this is the good solution, and this is the perturbed solution. Is this perturbed solution going to the uh, to the uh, to the reference solution or not? Is it going to the reference solution or not? This is the main question. Okay. Assume that the system is perturbed, let's say here, on a short time horizon. At the end of this action, initial conditions have changed. How does the evolution of the system change? Okay. You see here, T0 is about the initial conditions. Okay. So this is the reference solution. You compute it for the whole time domain, okay, mathematically. And this is at T0, the initial conditions change. The initial conditions change. And you have this perturbed solution now. Is this solution evolving by itself, going in some unknown direction, or is it drawn back? Is it drawn back to the continuous reference solution? This is the question. In other words, is the reference solution an attractor or not? Is the reference solution an attractor or not? Okay, so it says here this new evolution corresponds to a different solution called, okay, and this is called the perturbed solution. Does the perturbed solution stay close to the reference solution? Okay, so this here is the perturbed solution, and this here is the reference solution. Okay, the reference solution. Let's use a different color. Let's use red. So if the perturbed solution comes close to the reference solution, probably we'll call this stability. But if the perturbed solution veers off and has a different evolution from the reference solution, then probably this is related to instability. And now, if we think about what we discussed so far, who do you think will be in general the reference solution for a nonlinear system? what do you think we are going to consider a reference solution? Always. Who is going to be the reference solution? Can you tell me? Can you tell me? For every nonlinear system, most of the times, or in most cases, for many nonlinear systems, we have the so-called equilibrium. What is this? What is the equilibrium of a nonlinear system in terms of solution?
I would say point where the solution is zero, like that there's
No, actually, no. The equilibrium is not necessarily zero, but indeed where the dynamics is zero. But is this a solution of the system or not? The equilibrium, is it a solution of the system or not?
I would say yes, but I'm not sure.
Yes, of course it is. Of course it is, because it's the x star equilibrium point. If x star is zero, that means x dot is zero. So it is a solution. It's the trivial solution, if you remember. If we talk about the scalar system, these are equilibria. Parallel lines to the to the what? To the x t parallel lines to the horizontal axis, to the time axis. Okay. So yes, the equilibrium points, indeed, they are trivial solutions, if you remember. So instead of taking, who are we going to take the reference solutions from now on? Who do you think we are going to take as reference solutions to talk about stability? Who are we going to use as reference solutions?
The equilibrium point.
Exactly. So probably these are going to be the reference solutions. And then we are going to check if we change the initial condition, if the new trajectory comes towards the equilibrium or goes away from the equilibrium. And this is how we're going to define stability. Exactly. So we are going to use in this reasoning, in this argument of the perturbed solution versus a reference solution, and considering the stability, the capability of the perturbed solution to go to the reference solution, we are going to use as reference solution not just any solution we compute, because that's difficult, but we are going to use the equilibrium points as reference solutions. Probably. Let's see. And now we go to the very famous, probably you must have heard before, of Lyapunov stability. Lyapunov stability. So, Lyapunov stability is based exactly on this argument. One would like that small changes in the initial conditions should have, or must have, or would have, or could have a limited influence on the solutions. Okay? Continuous dependence on the initial, because we have continuous dependence on the initial conditions. So, stability is a property of the reference solution and not the system. Okay? Using this argument. Stability is a property of the reference solution. So the reference solution is called stable if disturbing the system, the new solution goes back to the reference undisturbed solution. Am I making sense to you? Tell me.
For me, it seems logical.
I think it's logical, yeah? Think about the pendulum. It's the easiest thing, it's the easiest way you can think of things. This is the pendulum, yeah? And the pendulum has this stable equilibrium point, okay? 0. So that means, all right, well, I can't show you in a plot because this is two-dimensional, okay? This is two-dimensional. Okay, and now we do a small perturbation of the pendulum. Assume this is very, very small. Perturbation. Disturbance. Right? So the new solution, swinging, in the end, it will stop where? At the equilibrium point, at the reference solution. That's why we take the equilibrium point. That's why I take the equilibrium point to be a reference solution. So I'm going to make the phase portrait, x2 versus x1, okay? So this is theta dot versus theta, if you remember, where theta is the angle. Okay, so this is the stable equilibrium point. This is the stable equilibrium point, true? And now I'm just disturbing the pendulum from that. So disturbing the pendulum from that probably will do something like this. So I bring the pendulum here in a different position. Okay. If the pendulum, if the equilibrium, if this is a stable trajectory, if this is a stable trajectory, okay, then a point is a trajectory in the phase, in the state space. Okay, a point is also a trajectory. Okay, so if this is stable, probably this behavior will occur. Okay, so it will come. Actually, I should draw this. I should draw this using green. Okay, so I'm disturbing my pendulum, negative angle and positive. Yeah, if I do this, this is the disturbance. So I bring it from here. I force it to come here. Okay, I force it to go there. And forcing it to go there, I see that if I leave the pendulum to swing, this is going to happen. This is going to happen. If the equilibrium, so I can call this equilibrium stable. I can call this equilibrium stable. So this position, okay, is the reference evolution, or the reference solution. The reference solution 0, 0, okay? Then doing the disturbance, I do the solution x1t, x2t. This is disturbed, okay? This is the disturbed solution, okay? So green is disturbance, okay? And the green solution, because if the equilibrium is stable, when t goes to infinity, assume that t goes to infinity, or t is very big, will go to 0 if this is stable. So I can call this trajectory here. So this here, yeah, this is a stable trivial solution. A stable trivial solution, reference solution. Am I making sense now? Huh?
Yes.
Guess so. Or at least I ought to. Well, let's go back to the theory. So consider the system z dot is ftz, depending on time, and consider z tilde to be a solution of 6 defined for any non-negative, or for any t larger than the initial moment t0. And the initial condition is z evaluated in t0 is z tilde 0. And we have the following definition. The reference solution z tilde t is called stable in the sense of Lyapunov. Lyapunov was a famous Russian mathematician, by the way. If in the 18th or 19th century or something like that, if for every positive epsilon arbitrarily small, there exists a constant delta depending on the initial moment t0 and epsilon, also positive, sufficiently small itself, such that whenever I have a new initial condition, z0, whose distance from the reference z tilde 0 is bounded by delta, then any trajectory, any evolution, any solution z, depending on the initial time t0, on the initial condition z0 and the time t, will come very close to z tilde for all the time t after the initial moment t0. Exactly what I said here. This is stability. So disturbing the pendulum from 0, 0, very, very small. I see it swinging, but it's very close, and all the trajectories are always smaller than epsilon. Okay? This is what happens. So this is the main definition. Of course, this is an epsilon definition, as we very well know. The epsilon definitions are not good for practice. So probably we'll need some very nice theorems and results to help us get some very nice checkable, so to speak, conditions we can easily verify to check whether an equilibrium point is stable or not. Okay, is stable or not. Okay, well, when delta does not depend on the initial moment t0, and this is what usually happens, we introduce the concept of so-called uniform stability. Okay, well, the dependence, it says here, on delta on the initial moment t0 separates the concept of stability between autonomous and non-autonomous. This is not among, this is between autonomous and non-autonomous systems. Yeah, you can check that if you look in the previous definitions in chapters 2 and 3. Okay, all right. And now, of course, we are going to concentrate on the stability of the origin as an equilibrium point, because we can bring everything to the origin. It's better to discuss only, to have the results clear for one very famous point, let's put it this way. Okay, and any equilibrium can be transformed very easily into or any system can be transformed to be a system with zero with an equilibrium point in the origin. So assuming system 6 is autonomous and z tilde be the reference solution in definition 7, we have an arbitrary solution fz, z dot is fz. We make this change of variables. X is z minus z tilde. X is z minus z tilde. Hence, in 0, okay, or you can just get the system in X, error deviation system. Okay, and you get this x dot is z dot minus z tilde dot. By definition, this is f, because here you get z is x plus z tilde. Hence, this is fx plus z tilde minus f z tilde. And you call this fx. So now you know that for x equal to 0, x equal to 0 is z equals z tilde. Okay, z equals z tilde. But in 0, this is true. This is already true because they have the same initial condition. Okay, they both depend on the initial condition. So this, hence, it's easy to see that f0 is 0. f0 is 0. Okay, right? Okay, so for x equal to 0, if x is z minus z tilde. Okay. Then z is x plus z tilde. Okay. So this becomes what? This becomes what? If I want to make 0 here. I want to make 0. Oh, yeah, this becomes fz tilde minus fz tilde. And this becomes immediately 0. Okay. Okay. So the origin is an asymptotic, is an equilibrium point of 7. The origin is an equilibrium point of 7. Okay. So if you have any equilibrium point, you can bring it back to the origin very easily. Okay. So it makes sense to make the analysis about the stability of the origin as an equilibrium point for nonlinear systems. Well, so the stability of the reference solution z tilde in this case is equivalent to the stability of the trivial solution x equal to 0. Okay, so now it's very good to understand what we discussed. I told you earlier we are going to use the equilibrium point as a reference solution, and moreover, actually, we are going to use the origin as an equilibrium point and the reference solution to discuss stability. Okay. Of course, we are going to concentrate the discussion on the stability of autonomous systems. Why does this make sense? Because even if you have a nonlinear forced system, you can always pick, if you want to stabilize and check the stability, you can always pick what is this? A state feedback and connect it here to U. And then this system is autonomous, and this becomes f of x, yeah, because U is alpha x. U is alpha x, okay? So it makes sense to discuss the stability of autonomous systems from a control perspective. Because you might wonder, or one might come and say, okay, but you told this is a nonlinear control system course, and you tell us about the stability of autonomous system. But the argument is that yes, indeed, because when you pick a state feedback, because everyone understands that stabilization of the nonlinear systems is done via state feedback, or even if it's output feedback, in the end, it will boil down to some state feedback. Okay? So if you pick a state feedback, then the closed loop system, yeah, this is closed loop, is an autonomous system. So it makes sense, it makes total sense, actually, to discuss about the stability of autonomous systems. Okay, so stability, we understand when we talk about stability, we actually talk about the stability of the origin as an equilibrium trivial solution, yeah, as an equilibrium point. The stability of the trivial reference, I would say here, to be more consistent. Trivial reference solution, I would say. And I hope you agree with me. Okay. Well, z tilde may also be a trivial solution if we talk about z tilde 0 as a. So we can take. There is no actually what this line says here is that there is no loss of generality using the origin. There is no loss of generality. because you can always talk about any other equilibrium point in the same fashion, taking the same coordinate transformation. Because you can take, if you have a fx, yeah, and you have the equilibrium point x star, fx star is 0, then you can always do the change of variable. X tilde, so to speak, is x minus x star, is x minus x star. Hence, x is x tilde plus x star. Okay? And taking the time derivative, you have x tilde dot is x dot. So x dot is now f x tilde plus in the new variable, yeah? X tilde plus x star. And you call this f x. Okay? And now f x is 0, okay, if you have x equilibrium point equal to 0. X, no, sorry, f, this, I forgot. And you have this 0, this is 0, okay? So that means that x tilde star, sorry, that means that x star, x equals x star, okay? Do I make sense? Do you understand? So if you change you take the variation with respect to the equilibrium point and rename your system like this, you can talk about the origin as an equilibrium point. Does it make sense? Does it make sense? Yeah?
I guess so.
Yeah. Because you do this change of variables. Okay. So at equilibrium, x like this is 0. At equilibrium, you get x equal x star. So it's the same equilibrium point. So it's correct. Okay. So it only makes sense, like I said, we have no loss of generality discussing solely or exclusively about the origin as an equilibrium point. And 9, now we turn our attention to the definitions of stability. Of course, we'll probably have some epsilon definitions, as we expect, and which is typical. Okay. So if you have a nonlinear system x dot is fx with the initial condition x of 0 is x naught, and if we assume that x star equal to 0 is an isolated equilibrium point, that is f evaluated in 0 is 0, then we have the following definition. The equilibrium point x star equal to 0 is called stable in the sense of Lyapunov if for any positive epsilon there exists a constant delta depending continuously on epsilon, also positive, such that whenever the norm of the initial condition is smaller than delta, then, okay, if you have an initial condition whose norm is bounded, then the trajectory, depending on time and that specific initial condition, is also bounded. Okay, it's also, so it's not infinite. It's also bounded for any t non-negative for any moment in time. Of course, unstable if it's not stable. Asymptotically stable in the sense of Lyapunov, okay, is stable and an attractor. Stable and an attractor. You remember the definition of attractor from the first order case. Okay, so the equilibrium point x star, sorry, equal to 0. So the origin is a stable equilibrium point, asymptotically stable equilibrium point, of course, in the sense of Lyapunov. We are not going to repeat this in the sense of Lyapunov any longer because we understand now. If this is true. If there exists a positive alpha, and now we have also a new notion of stability. If there exists a positive alpha and a positive beta depending on some delta zero, which is the bound of the norm of the initial condition x0, then then the solution satisfies if the solution satisfies this exponential boundedness condition, we call the equilibrium point exponentially stable. And now let's give the example of the linear systems. Linear system. Let's take it scalar first. Linear scalar system. Okay. As a special case. Yeah. X dot is AX, whose solution is explicit. Yeah, we know that with the initial condition x naught. So is e a to the power at x naught. And now we have the discussion. About a. If a is zero, then x is x naught. So we have stability in some sense. If a is larger than 0 and constant, okay? So nothing happens. If a is larger than 0, then x of t goes to infinity as t goes to infinity, so it's unstable. And condition number, this condition, of course, we are now in the situation number 2. Because this grows, this condition never happens. And if a is, okay, negative, if a is negative, then xt goes to 0, t goes to infinity. But who is 0? From this system, equilibrium point is x star equal to 0, unique. This is the unique equilibrium point. So for a negative, 0 in this case, and now we can show this plot. 0 is an asymptotically stable equilibrium point. 0. Yeah. So this is the reference. Trajectory. Okay. It's asymptotically stable. If x is 0, if a is 0, sorry, and you start here with the initial condition x naught, then you stay here at constant distance from the initial condition. You're still stable. But if a is positive, okay, if a is positive, actually I should do this drawing in a different way. Let me show you. So this, I must have an initial condition. Okay. So this is xt, this is t. Assume I have here an initial condition. This is x naught. So this is for a equal to 0. This is for a larger than 0. And this is for a smaller than 0. But here, since this is a global solution, you can say that stability is not of this trajectory, is not only of the trajectory here, but is the property of any trajectory. Okay? Because even if I change the initial condition and I move it here, if it's stable, this also happens. If I change the initial condition here, okay, this also happens. Okay, so in this case, in this very simple case of linear systems, this is a global problem.
Can you hear me? Hello?
Yes, hello. Yes, yes.
Yeah, a power failure. And the PC where the call was open was off.
It's okay. I see that recording it's still working. And
oh, that's nice. Okay. That's very nice that if it can do that and these things do not count. Sorry about that. Power failure, okay. Where was I? First of all, share screen. Can you see my screen now?
yes, now I can.
Okay, fine. So we were discussing we were discussing the stability of the linear system. Okay, you can see it, yeah?
Yes, it's fine. I see
Okay.
it.
Okay. Right. So we have this epsilon delta definition. Okay. It's very clear. Okay, in the sense of Lyapunov. stable if the trajectory is bounded, okay, no matter what happens to the initial condition. Unstable if the trajectory probably, or the evolution, the solution is not bounded, okay, and veers off crazily, okay. And asymptotically stable if actually the solution will go asymptotically using a limit, will go to the reference solutions, just like we mentioned, okay, just like we started our analysis. Of course, to be able to determine this, we have to do a specific analysis. When is a trajectory, or under which condition a trajectory or a solution can go to the reference solution, is attracted by the reference solution. And from now on, we are going to build an energy-based argument. And for that, we need what's called Lyapunov functions. Lyapunov functions are a main tool in the stability analysis. So the idea is like this: if the total energy of the system decreases along the motion, okay, along the solution, being minimal at the equilibrium point, then each evolution will approach asymptotically the equilibrium point. Okay. So they said that Lyapunov in 1982 introduced a class of functions which play the role of the system energy instability analysis. These are Lyapunov functions. Please note that these Lyapunov functions, they are not necessarily physical energy functions. We are going to see that. For instance, a linear system can have, we can define an energy in not necessarily in the physics sense. That's what I'm trying to tell you. Okay. So this is very not restrictive in some sense. You have a lot of freedom to determine a Lyapunov function. Of course, this is very difficult, because that means that to get a good Lyapunov functions, to prove that your equilibrium achieves stability, is not at all an easy task. Is not at all an easy task. Okay. Right. So, for instance, for the pendulum, we have this total energy for the pendulum system. This is the kinetic energy. So this part is the kinetic energy. And this part, yeah, using ML as well. This part times this guy. This is the potential energy. This is the potential energy. Okay. What can you notice about this function? First of all, what's something peculiar to this function? What's something peculiar to this function? Can you notice? How is this function? X squared and 1 minus cosine of x1.
Non-linear.
Okay, nonlinear, I agree. But more than that, the values of the function, how are they? They're always
Positive.
Always positive, exactly. Always positive for all x. For all x. This is very important. This is actually crucial. This is crucial. So probably these Lyapunov functions must be what we call positive definite. They must be positive definite. Okay, Lyapunov functions. And what happens to this energy? Think about the swinging pendulum. Think about the swinging pendulum. What happens to this?
It decays.
It decays, exactly.
Yeah.
Exactly. So the pendulum is swinging back and forth, and slower and slower. Why is it decreasing? Can you tell me?
Because
what's causing the decrease of energy?
Some friction.
Exactly. Because of the, how do we generally call friction if we talk generally about all systems? electrical, mechanical friction, or we call it, what happens to the energy? When energy is lost or wasted, how do you call that? You have DC, dissipation, right?
Dissipation. Yeah, yeah. So,
Exactly. The energy is dissipating. So that's what happens. If you have some friction, probably the energy is dissipating and is decreasing to some constant or zero level. We don't know whether it's zero or not. Probably here it's zero, of course, but it's constantly decreasing. Interesting. Very interesting. So probably we'll have to check the evolution, because the energy is a function of time, okay? So this is E total of time. Yeah, it depends on the time. So probably we have to check this property. How is this? Right? Or actually we call it E dot. Yeah, we have to check this. We have to check this. And of course, to have the energy decreasing, you probably need this, I don't know, to behave something like this. True? Probably need this. We know from this is a scalar function, by the way. Yeah. So E tot here is defined on R2 and valued in R. So this is a scalar function. Okay. So probably if this happens, then how is E with respect to time? Decreasing, right? Because the derivative is negative. E is decreasing, indeed. So we have to understand these concepts. Okay. So we have to understand the concept of derivative along the trajectories. So essentially, yeah, it's written here. I don't need to write any longer. Consider any function v, and we are going to use the notation v exactly in the systemic perspective that it's not a real energy. Okay. So when we talk about energy functions, they are not necessarily physical energies. They can be just made up. You can make up a function, quadratic, degree 4, doesn't matter. You make it up. If it's positive, definite, and it's 0 in 0, then you can call it an energy function, a Lyapunov function. Okay, so it's an abstract expansion, if you like, abstract, non-trivial expansion of the idea of energy function, of energy. Okay. So we have a function v continuously differentiable on a domain containing the origin and verifying this condition. Verifying this condition. Okay. If x t z is a trajectory, is an orbit of this system, then the derivative of v along the trajectory is called orbital or Lie derivative of the vector field v is given by, and this is, you see the variation with respect to time, because v is a function of time. Okay, so it's v of x of t, so it depends on time. The variation, the time variation, the dynamic of the Lyapunov function v, we compute it like this, and we use here for derivation, if you remember from your first year math classes and courses, this is the Leibniz rule of derivation, because you have a composition here, v composed with x of t. Yeah, it's like this, something like this. And we have the rule I show you for scalar. So f g x is f g x, and if you take d dx, d to dx, then d of f composition g with respect to x in the point evaluated at point X is actually dfgx with respect to X, and is what? Is df dg evaluated at point X. No, sorry. Evaluated at point G. So evaluated in Gx multiplied by dg dx evaluated in point X. Okay, or shortly f prime gx times g prime x. Am I right? Yes or no? This is the Leibniz rule. So applying these Leibniz rules, essentially, so dvxt to dt is the partial derivative because we have more variables, so we have to use the partial now. So is dv dx to the power x. This is the gradient of v. This is the gradient of v with respect to x times dx dt times dx dt. So when you multiply, what's the gradient? If you have vx, yeah, v defined on Rn to R, okay, differentiable, smooth, whatever, okay, then the gradient dv dx in x star, any point x star, any point x, whatever, a, any point a, call it a, okay, sorry, is dv dx1 in point A, dv dx2 point A, okay, dv dxn in point A, okay, where A is a1 up to an, also a point Rn. So this is the gradient. This is the gradient, okay? I just remind you from math, okay? And this, if you multiply this now, dv dx in x, multiplied with x dot is x1 dot, x2 dot, xn dot. This is dv dx1 in x, dv dxn in x, multiplied with x1 dot, x2 dot, xn dot. This is dv dx1 times x1 dot plus dv dx2 x2 dot plus dv dxn xn dot. That's why you get this relation here. So I just explained this relation here. But this x1 x dot n, this is fx. This is fx by the definition of the system, yeah? The system is x dot equal fx with the initial condition x naught. So you get this very nice relation, the Lie derivative. Yeah? And this is a notation here. You have this notation. This is from the Lie. This is a geometrical notation, a differential geometric notation. Okay. So this is the relation example. Example. Vx is half x1 squared plus x2 squared. This is positive for all x. Quadratic even. This is actually, if you have the vector x1, x2 in R2, this is half x transpose x. True? Because it's actually x1, x2 multiplied with x1, x2. And times half. Okay? Right? And you have that x dot is fx. This is f1 x, f2 x. So dv dt is what's dv dx1 dv dx2 times x dot times x dot. And what is this one? What is dv dx1? The derivative of v with respect to x1, how much is that? How much is that? Huh? How much is that? What's dv dx1? Tell me, please.
Partial derivative with respect.
Okay, understand. And how much is it? Because Vx is half x1 squared plus x squared. So, how much is it? You have V here. This is V. So, how much is dv dx1 and dv dx2?
It's x1.
Like this, true?
Yes.
Times x dot. So, this is actually x transpose fx. It's actually x transpose fx. Okay. This is, I would say, simple first year math. Okay. And now we have to understand what positive and negative definite functions are. A function v defined on a domain of Rn valued in R is said to be positive or negative definite if Vx is positive for all x less than the point 0, all x less than the origin, and negative positive definite and negative definite if you have this, and non-negative or semi-positive or semi-negative or non-positive, non-negative definite if the strict majorization or minorization sign is replaced with a non-strict sign. And you have an example here. You have an example here. V defined on R2 valued in R. Vx is this. I said earlier this is half x transpose x. You have this linear system, you have this matrix A, then dv dt is dv dx fx, yeah? Fx is ax in this case. So this is x1, x2 times ax. And how much is a or a times x? A times x is minus x1 minus 2x2. So this is x1, x2 times minus x1 minus 2x2. And this yields this result. How is W? How is W? Well, V is indeed positive for all X. And W is actually negative for all X. Negative definite. Okay. All right. You agree? And now we now have the main result. And we stop here and try to do example. Consider a nonlinear system x dot is fx, where f is nicely defined with the equilibrium point in the origin. Okay. If there exists a continuously differential function v defined on a domain D, valued in R, such that in the origin the function is 0 and v is positive definite for all the non-zero values of x on the domain D, such that v dot denoted by w is non-positive definite or is non-positive definite, yeah, or semi-negative definite. Okay. Or semi-negative definite on D, then the origin is a stable equilibrium point. Furthermore, if under the same assumptions as above, W is negative definite, in a ball centered in the origin, not necessarily on the whole domain, but at least in a ball centered in the origin, then the origin is an asymptotically stable equilibrium point. Please note that these are all sufficient conditions. Okay. Oh, it says here, they are only sufficient conditions. If you didn't find the Lyapunov function, that doesn't mean that it doesn't exist, or it doesn't mean that the system is, or the origin is not stable. Doesn't necessarily mean. That means you didn't find the proper Lyapunov function to do it, or maybe it doesn't even exist. Okay, doesn't even exist. All right. A function v satisfying the conditions of theorem 9 is called the Lyapunov candidate function. Okay. A Lyapunov candidate function. All right. So if a given Lyapunov function does not satisfy the conditions of the theorem, we cannot conclude that the origin is not stable. Okay. It's just we didn't find the proper Lyapunov function. Can you still see my screen? Huh? Yes, sir. Oh, yeah.
Yes.
I can also see my screen, so I'm fine with it. Yes. Okay. All right. So this is the main powerful, wonderful result of Lyapunov. I just have to tell you that if you browse through the book of Khalil, there are some control algorithms, some control procedures based on this Lyapunov theory. One of them is called energy or passivity-based control, because passivity, that means decreasing and losing energy, or systems which do not actively produce energy, they are passive, just like the hot light bulb. The hot light bulb, it used to be a passive device, right? A resistor is a passive device. So the same can be applied to physical systems, and not only physical systems. They can be passive, and passivity under specific circumstances induces the stability of the origin, because it's based on the decrease of the energy, just like in the case of Lyapunov, of the Lyapunov theory. And essentially, all the proofs in some or most of the nonlinear control techniques, you can check that out, and I can put you other material. For instance, I have somewhere a material about stabilizing the drone with linear stuff, but doing some nonlinear Lyapunov theory analysis. You can see that this result is really, really, really powerful, and it's actually the only, pretty much the only fundamental result that people use today in nonlinear control. Okay, there is variation, there is new stuff, and so on and so forth, but the fundamental result is this one. The fundamental result is this one. Okay, let's go back to this example. Let's go back to this example, and then let's make it a little more general. So you have x dot is, say, lambda 1, 0, 0, lambda 2. Okay, lambda 1 and lambda 2 belong to R, real numbers, times x, sorry. Okay, and like I said, you build the Lyapunov function Vx is half x1 squared plus x2 squared. Okay, this looks like physical energy anyway. Yeah, kinetic and potential energy. Yeah, of course, using quotes. This is not for real. Fx is lambda 1 x1, lambda 2 x2. Okay. Okay, fine. Then v dot x is dv dx fx. We just said that. So it's x1 x2. This is dv dx, the derivative times fx, lambda 1 x1, lambda 2 x2. So this is, it's lambda 1 x1 squared plus lambda 2 x2 squared. Now, discussion. It's very interesting because we know some things for linear systems. For instance, if one of the eigenvalues is 0, okay, lambda, say lambda 1 is 0, okay, you still have wx is v dot x is lambda 1, lambda 2, x2. So if lambda 2 is negative, okay, then you still can have 0 is stable, but is not asymptotically stable. Not asymptotically stable because you don't know what x1 is doing. Don't know what x1 is doing. Okay, this depends only on x2. Okay, this depends only on x2. Don't know what x1 is doing, so this is only stable, not asymptotically stable. Not asymptotically stable. Okay, it's just stable. Even if lambda 2 is negative. Even if lambda 2 is negative. Okay, because now you have that x1 is 0 actually. X1 dot, sorry, is 0. That means that x1 is constant, so it's not 0. So you don't have 0, you don't have the origin. You don't have the origin as the unique equilibrium point this time. Of course, for x1 equal to 0, you can get again the origin, but x1 is constant. Okay. Now assume that both eigenvalues are different from 0, are non-zero. lambda 1 positive, lambda 2 negative, say, you get what? Then Wx has no sign. There's no sign. Okay? There's no sign. It's not necessarily positive. Has no sign. So we can't decide. Cannot decide too well. But we know it's not stable. Probably not stable. We know this from linear theory. Now, if lambda 1, lambda 2 are both negative, then Wx is negative, then indeed 0 is asymptotically stable, and we know that from linear systems theory. We know that from linear systems. Okay, this is very nice, and so on. You can check yourself furthermore. You can check yourself all these things. You can check yourself all these things. For the pendulum, we have this Lyapunov function. Why do we write it 1 minus cosine x? Because 1 minus cosine x, 1 is actually twice sine square what? Something like this. It's like this, right? You agree? It's like this. All right. So this is where this 1 minus cos, and if x1 is between minus pi and pi, then 1 minus cosine cos x1 is always positive. Is always positive. Actually, yeah. Okay. Then 1 minus cos is always positive. So this is a positive definite. This is positive definite. V0 is 0. That makes sense because cosine in 0 is 1, and 1 minus 1 is 0. So this is true. And V is positive definite on this domain. And the derivative is this guy. The derivative is this guy. Is this guy. You know. So this is not negative definite, but semi-negative definite. So we have a problem. Because from this one, it means the origin is only stable. But we know from chapter 3 that the origin is asymptotically stable. Is asymptotically stable. So what do we do? What do we do? Okay, and this actually, the analysis was wrong here because indeed this is not negative. This is semi-negative definite. Okay. Okay, and actually here we should have a question mark because we don't know. We know it's not stable in the. Okay. So for which values? Okay. For which values is this negative definite? Which values of x1? And I said x1 can be anything this time. X1 can be anything this time. Okay. So we don't know. But we know that the origin is asymptotically stable. So we have to prove that somehow. Okay. We also have, if you remember, the mechanical oscillator. I'm going to take the linear version of that. Mechanical oscillator. Okay. mechanical oscillator. Y double dot plus B Y dot plus K Y is 0. Remember that. B and K positive. True. And we have x1 dot is x2 because we make the notation x1 is y, then x1 dot is x2 is y dot, and x2 dot is minus k x1. I forgot about the mass. I'm taking mass 1 because I don't care about the mass. Minus b x2. Okay. Yeah. And the energy here is half. The mass is 1, so x2 squared plus probably k squared x1 squared, something like that, or kx1 squared. Okay, from the elastic force. This is the potential energy, kinetic and potential. Hence, okay, equilibrium points. I forgot here. Equilibrium points. X2 equal to 0. X1 equal to 0. So the origin is an equilibrium point. Okay. X star is 0. The origin is the equilibrium point of this guy. Right. Good. So we have v dot x is k x1 x2 times x2 minus k x1 minus b x2. So this is k x1 x2 minus k x1 x2 minus b x2 squared. They cancel each other. And this is again like this for all x, all x1. So the origin is stable. Based on this theory. But from chapter 2, yeah, we know this can be a node. Chapter 2, 0 is an attractor. 0 is an attractor. Do you remember that? We used to say that. 0 is an attractor for this guy. Right? We used to do the linearized stuff. A is df dx. This is the Jacobian in 0. And that is what? 0, 1 minus k minus b. Agreed? You agree? And we had the characteristic equation lambda squared minus b lambda plus the determinant, and that was k plus b, sorry. This is 0. And this is a Hurwitz polynomial. Why? Since b, k are positive and there is no change in sign. I remember you, the Hurwitz criterion. Okay? That means lambda 1, 2 in the complex left half plane automatically. Okay? Delta here was b squared minus 4k. B squared minus 4k. True. So assume this is negative because I like the complex conjugated stuff. So you get lambda 1, 2 is minus b plus minus j square root b squared minus 4k over 2. This is a stable focus. Stable focus. Asymptotically stable because it goes to 0. Right? It goes to 0. So yeah. Where is it? So where's asymptotic stability? Is this different from this? Of course not. Of course not. It's not different. It's still asymptotically stable. We need something more. We need something more. So I showed you two types of very nice analysis, stability analysis. And the link between this is going to be the so-called principle of LaSalle. There's three scientists who found out something very interesting. Essentially, they're saying if the energy is constant only at equilibrium, if the decrease in energy is constant only at the equilibrium is asymptotically stable. And we have to prove that. We are going to do such a proof using invariant sets. Invariant sets. Okay. Listen, I'm not sure. I don't know how you feel, but I think it's a lot of information. Would you agree to stop here, or do you want more? What do you think? I'd like to hear your opinion on this.
Yeah, from my side.
I can't hear you very well. Can you repeat, please? Andrei.
I agree with you.
You agree? Radu?
Yes, I don't know. I'm somehow more familiar with.
You're more familiar. For you, this is a recap, essentially.
Yeah, maybe I don't know. Maybe Florian.
Yes, but you're the only one who have seen these things before.
Yes.
I'm not sure about Florian, but I'm sure that Theodor and Andrei have not studied this before. I'm not sure about Florian, if he saw these things before, probably in a different context. Florian, how do you feel about these things? Would you agree to stop, or would you like to see some more? The slides are here. You can read the OneNote notebook anytime, so you can look in advance. All the slides are on Moodle as well.
Yeah, sorry, I was
How
parallel.
do you feel about it, Florian?
I didn't hear the question because I'm parallel in a Romanian language course. That's why it's a little bit difficult for me to know what's going on right now. What was the question? Sorry for.
But I'm talking only English, so where's the Romanian in this? I'm not
No,
sure.
I'm in parallel right now. Like from 4 p.m. I have a Romanian language course, which is like intersecting
Romanian language course. Oh, that's lovely.
That's
yes,
why I'm
so
just like hearing on one ear.
So my question was if it's enough information for today, and you would agree to stop. And the question was, if you saw these things before, if you studied these things such as Lyapunov and these things before.
Yes, as far as I can remember, I had some introduction to Lyapunov in Germany, but like for me, like I know some of the equations you showed before, like asymptotically and so on. And we had some like pictures and drawings showing it how it's working, so nearly the same as you showed it, but not like in a sense that we like calculated
so
anything.
Probably not so advanced and not so detailed, probably.
Yes.
Yeah.
But
so I think, yes.
Yeah.
Please.
I think at least I get like the main idea behind Lyapunov, and to get a better understanding, I think I will have to like look at it again and read in a book or so.
Exactly. Read in the book of Khalil, that's very nicely explained, and these slides and also examples we'll see next week. We have a lot of examples in Maple, and also you can put them in MATLAB if you do not understand Maple. You can translate those examples in MATLAB yourselves. And there is also an assignment. So yeah, I'll also try to find the material about stabilization of the drone, of the angles of the drone or angle movement. I think there is something related to Lyapunov as well, because this is also a nonlinear problem. So I have to check if there is a very nice reference I can give you to study for this. Okay, then we'll stop. And then I'm going to say, if you have any questions, comments, or remarks, please, before we say goodbye. I'm listening.
Maybe I will ask what's next, like summary.
So, Radu, I have to finish all the things that you have seen at the nonlinear systems course 2 years ago or 1 year ago. So I'll continue, as you know, with absolute stability as an application. But in addition to this, there's going to be 2 or probably 3 lectures on feedback linearization, which is something you haven't seen before. This is new. So there is a 6th chapter called feedback linearization. This is a typical nonlinear control technique, which I would like you to study. It's kind of difficult because it's based on a lot of differential geometry. I'm just going to give you the hints about it, and you'll have to study it and see how it goes.
But I see some types of control, like you have the Lyapunov function V.
Yes.
In V, you have some things that you can tune or decide their signs and stuff. And based on that, you somehow create a controller that's...
Yes, that's true.
Non-linear.
So you can have degrees of freedom in the Lyapunov function as well.
Yes.
Just like a PID controller. Actually, I have a friend. If you people can look it up on the internet, a friend of mine from Greece. I'm not sure if he's still in England. We used to be colleagues in the UK. George Konstantopoulos. He's a Greek guy. He's doing a lot of nonlinear integral control, and that's actually nonlinear PID controllers. They're also based on Lyapunov theory because you have to prove closed loop stability. There is no other way to do it. Okay, they use all these concepts of input to state stability, something to something else stability, but they're all based on the same fundamental ideas of Lyapunov theory. And George used to do that for power electronics. You can look up his papers and study and see the effectiveness of Lyapunov theory for these things. So nonlinear PID control. Essentially, when you do nonlinear PID, just like Radu was telling us, you have to tune something. Indeed. And also in other Lyapunov things, you can tune specific parameters. Have you seen this in practice, Radu? Have you worked on this type of controllers?
No, I've just seen like also some course material on Google, like out of curiosity.
I see. Right. So this is yeah, I agree. So yeah, you can look up. There's plenty of applications. You know. And actually, also feedback linearization is touching, even if it's a geometrical differential geometry tool, it's also needing Lyapunov stability to prove the closed loop stability. You know. So essentially, most of the nonlinear control techniques classic nonlinear control techniques. They're all variations of the same idea of Lyapunov theory as fundamental idea. Of course, they have other sophisticated things inside, you know. Yeah. Okay, other questions and comments, please. One more thing, please. Please do the assignments, okay? Like I said, I'll leave them open until the end of the semester. I'll check out to see if all of them are open. I guess I think I opened all of them until the end of the semester. I'll check it again. Please do the assignments to get the points, okay? Agreed?
Yes.
Okay, fine. Well, and if there's anything else I can help you with, please let me know. I'm listening. If there's anything else you need me for, please.
For me, it's fine.
All right. Then I'll see you next week. Thank you.
Thank you.
Where do I stop the recording? Because I need to stop the
Thank you.
recording.
Goodbye, teacher.
Thank you.
Sure. Do you know, can you tell me where
I
I
think it will stop automatically when
Oh, it'll stop
when
automatically.
we close the meeting. Oh, here. Oh,
Oh, yeah.